We're the most important experiment in the world.
There you go. You see the flickering of the plasma, we are creating fusion here. This is our little sun. The temperature is 10 times the core of the sun. It's extremely hot.
200 million degrees. That is the temperature of the sun being built here on Earth.
So fusion really is the perfect way to make energy. I mean, we have millions of years worth of fuel. It produces no long-lived radioactive waste.
If we can solve the engineering challenges, energy will become cheaper, more available for everybody.
The problem with fusion is not what it will be, it's getting there. We've had to come up with some very clever ideas to hold something at 230, 250 million degrees. I mean, that's astonishing.
So this is JET, the largest magnetic fusion experiment on Earth.
JET is the Joint European Torus. It's a donut-shaped containment vessel that confines a plasma at a temperature of about 230 million degrees.
We actually create a little star here in this machine every day, every 20 minutes.
To reach these temperatures, JET uses beams of high-energy particles. They transfer their energy to the plasma. But the second heating method is more familiar.
In order to really heat up the plasma, we also have little microwaves. The red and blue lines around the machine are our radio frequency heating, where we are using these waves to heat up the plasma. Conventional microwave is about 1000 watts. So these, actually we have about 6,000 to 8,000 little microwaves hiding inside these pipes to really heat up our plasma.
When the first plasma was produced in JET, it was not of the temperatures necessary to get fusion. Gradually we learned from that. We learned how to hold the plasma in a magnetic cage, and the cage keeps it from touching the walls so that we can take it up to these incredible temperatures.
Most of us are familiar with the more traditional nuclear power station. It uses fission to create energy. Fission is the exact opposite of fusion.
Because in fission you have a large particle that you try to separate, but in fusion you have two tiny ones that you are trying to fuse together, gaining a lot of energy.
Plasma consists of two kinds of hydrogen. Right? There's heavy hydrogen, which we call deuterium, and the super heavy hydrogen, which we call tritium. And when they're running around at these temperatures like 200 million degrees, they bang into each other with immense speed. And when they do, and they get close enough, what we call the strong force, which binds the nucleus of atoms together, grips them, pulls them together, and they fuse, and they make helium, and they spit out a neutron.
These are very, very large energy neutrons. So we are just waiting for the next experiment. It's going to happen in 10 seconds. This is where the magic will happen. These are our windows into the tokamak where you are going to see the plasma. Starting now. So we started the plasma, there you go. You see the flickering of the plasma, we are creating fusion here.
Holding a plasma with a magnetic field is a bit like holding a lump of jelly with some knitting wool. Right? It's not a very good way to do it, but it's the only way we know how to do it, so we have to make it work.
And making it work does mean the material scientists have a big job on their hands.
Fusion energy is a materials challenge as much as a plasma challenge, because you've got to get the plasma really hot, but once you've done that and can keep it there for a long time, it spews out lots of neutrons with lots of energy, and that's what you want to get electricity. But then those neutrons hit the materials that surround your plasma.
Now that neutron plows into the wall, and when it gets into a piece of steel, it will collide with the nucleus of one of the iron in the wall. And that iron nucleus will plow through the steel, making kind of jiggling up all the atoms inside the steel. The question is, can we make steels that remain robustly strong despite being bombarded by neutrons.
We're in the new materials research facility at Culham. A particular feature of it has hot cells to handle radioactive material with manipulators.
But the relatively low levels of radiation produced by fusion compared to nuclear fission mean that pieces of metal smaller than the tip of a pin that have been bombarded by the neutrons can be cut and analysed.
We are, with our gallium ions, digging trenches on a very tiny scale, which is about the thickness of the 20th of a human hair. There's a micromanipulator needle which is brought in. We then glue this bit of material to the micromanipulator and free the sample out from the matrix. And this bit of material can now be taken off-site for further analysis, where the overall activity levels of the sample is heavily reduced because of the very tiny size of the material.
Studying the impact of the neutrons on the metal structures is all about fine-tuning the reaction within JET to increase the energy output. It has led to crucial changes to the materials used for the internal tiles on the wall of JET. The biggest change was to swap the carbon tiles for beryllium tiles.
One very important thing in fusion is to keep the environment very clean, because we are using hydrogen isotopes that are have only one proton. But as soon as you get some dirt in from the vessel, it loses all the energy and it dies.
The wall of JET, when we did 16 million watts, was made of carbon. And it turns out carbon makes a lovely wall, except for one thing: it absorbs the fusion fuel. And we can't have that in a reactor. So what we've done is we've designed a new wall which is made all of metal. It's made of two kinds of metal: beryllium, which is a very light metal, and tungsten, which is a very heavy metal.
So beryllium is a really good material to keep the inside of the vessel clean, much better than carbon. And this is why we changed 4,000 tiles 6 years ago with the robots.
We have a remote handling system here that we've developed over many years. We use that capability to keep people out of the machine, to protect them from the radiation. You can see that on the image behind the boom moving around. The simulation that we're using there is in real time, so as the equipment moves for real, it's matched on the simulation.
Changing the tiles brought about a step change in the power output of JET, but there was still one crucial problem.
Okay, so we made 16 million watts of fusion power, but in order to sustain the reaction, we had to pour in 24 million watts of power into the plasma to keep it at that temperature. So while we've done fusion, what we haven't done yet is self-sustained fusion. We want to light the fire. What we've got at the moment is we've burnt some fusion fuel, but we've burnt it by pouring in more energy, in fact, than we got out. We're getting out 16 million watts of energy, and we were putting in 24 million watts. So the next big experiment, the experiment that's going to take place in southern France, called ITER, that experiment will do something absolutely remarkable. That experiment, we will get it up to these temperatures, the fusion will start, and the fusion will produce enough heat to sustain the reactions. And therefore we will not have to put heat in to keep it burning. ITER
is the first experimental fusion reactor. It is the next step in our ambition to create clean, unlimited energy. It is being built in France. It is the most expensive science experiment on the planet. Only the International Space Station is bigger.
The case with fusion is that size really matters. As soon as you go to a bigger size, it will be a huge step change, because it will be able to keep the heat, and after a while it will sustain the fusion reaction itself.
So that's like lighting your fire. Once you've lit your fire, you don't have to keep the match on it, because it produces enough heat to sustain the burn. And when we do that with fusion, It will be the most historic moment. I think it's going to be the most important experiment of the 21st century.
I definitely think that fusion is going to happen in my lifetime. It's happening here every 20 minutes.
It's never going to be entirely free, of course. It will have its issues, the waste, etc., but they're much more handleable and manageable than today's power stations.
The plan for electricity is to try and get electricity by the middle of the century, by 2050. First electricity. That won't be commercial electricity, because first of a kind is never, commercial. But there's a deeper part to this question, and that is, when do we need fusion to work? So if we are to stop using fossil fuels and to fully transition into a sustainable energy economy by the end of the century, we've got to make either solar or advanced nuclear or fusion work, because there are no other ways to power the Earth.